In developing the DYN Servo control, one of the key performance factors is the servo response time given an instantaneous step command. The overall goal is to achieve the fastest rise time with no overshoot. The step response is an important specification for the servo as it tests dynamic relationship between acceleration and torque. Using development tools, we can first simulate the command and response according to different gain and inertia ratio values, then compare and verify using a real system. This is the high-level simulated structure of the DYN servo control loop. A signal is fed into the position command with 16,384 points, equivalent to 90-degree amplitude. The reduced H servo control block outputs a torque command to the torque servo loop. The torque servo loop block reads the torque command and outputs a corresponding real torque to the servo motor. Then finally, the inertia block, which simulates the physical motor and inertia ratio, outputs the physical angle response, which is converted into the final position response. The reduced H servo control contains the main position and speed servo calculations using proportional, speed, and integration gain parameters. The torque servo loop realizes the required torque using the command from position servo loop and motor constants. The inertia block simulates the physical motor and shaft response. Its input is a real torque command and output is the physical motor shaft angle. The acceleration is converted into position and fed back into the servo block. In our test system, the step command is generated internally within the servo drive. The final position response and rise time is measured as the time needed for the motor to reach from 10% to 90% of target position. Throughout this demonstration, we will be using the DST 400W motor with the DYN4 servo drive. The real system is directly coupled to various inertia wheels. The simulated system is modeled with this motor and various inertia characteristic parameters. We start with zero inertia ratio, meaning the motor shaft is free. Here is the real response. We can see the real system is very close to our simulated model. The response or rise time is very quick at approximately 11 milliseconds. The specialty of the DMM servo is not just its fast response speed, but also its adaptability to higher inertia ratios. As we increase to a higher 8 times load inertia, the servo can maintain relatively the same performance.
Okay, this is 2 Hertz.
The response time for 8 times load inertia is about 16 milliseconds. As we increase the inertia load even higher, the response becomes longer, but the servo still has no trouble maintaining fast and stable control. Here is a real system at 14 and 25 times inertia.
This is 2 Hertz.
At 14 times inertia, the rise time is 19.5 milliseconds. At 25 times inertia, the rise time is 24.5 milliseconds. These inertia loads translated onto a conventional ball screw system has the following load mass capabilities. For example, at 25 times inertia, this means the DMM servo can accurately and instantaneously accelerate and decelerate a 1400 kg load in 24.5 milliseconds with 1.25 mm amplitude. The capability of the DYN servo can be extended into even higher inertia ratios and higher frequency response operating regions. The control can maintain accurate response even up to 93 times inertia ratio. At 0 times inertia or free shaft, the control can maintain full displacement until 20 Hz frequency. At 8 times inertia, 15 Hz can be achieved. At 25 times inertia, 10 Hz can be achieved.
5 hertz, 8 hertz, 10 hertz. Stop.
For more information on these or other servo performance specifications, please contact us or visit our website.